Hello, everybody, and welcome to another great day of chemistry. So today we're going to be talking about why do I always have leftover food in my fridge? Because it turns out that chemistry is a lot like cooking for people, in that whenever I'm trying to make something, I almost always have to worry about not having enough of one of my ingredients or one of my reagents. So for example, when I'm making hot dogs on a bun, I need hot dogs and a bun. But part of the problem is, as many people have pointed out before, hot dog buns come in packages of 8 and hot dogs come in packages of 10, which means that if I'm going to make hot dogs, I almost never have enough buns. So in this case, buns is the limiting reagent. It limits how many hot dogs I can make. And in order to make more hot dogs, I need to get more buns. But then the hot dogs themselves become limiting. And this is a very common feature in chemistry, is that I almost never have enough of both reagents for the reaction to go to completion. I almost always have one of the reagents limiting and one in excess. And one of the big features of chemistry is figuring out which one of my reagents is limiting. So let's go ahead and try and look at a couple of the key ways you can try and determine what a limiting reagent is. So students I know typically like one of two major approaches. So the first of which is trying to figure out the number of moles of each reagent that's present and then compare this to the stoichiometric ratio. So let's go ahead and look at that reaction of solid zinc and hydrochloric gas in order to produce hydrogen gas. So when doing this reaction, it turns out I need twice as much HCl as I need zinc. So if I have equal amounts of HCl, then I'm going to need more HCl. If I have 3-to-1 HCl, then I'm going to need more zinc to react that extra equivalent of HCl. And so you can go ahead and compare how much your actual ratio is versus the stoichiometric ratio. The other major approach is you can say, I've got X moles of zinc. How many moles of hydrogen will that produce? I've got Y moles of HCl. How many moles of hydrogen will that produce? So whichever of my reagents produces more H2 is in excess. It can make an excess of hydrogen. Whichever one produces less H2 is going to be my limiting reagent and will determine exactly what my theoretical yield of hydrogen will be. So let's go ahead and work an example. Let's say I've got 100 grams of zinc and 100 grams of HCl. I mix them together and I want to try and figure out which one's going to be my limiting reagent. So let's go ahead and take a look at zinc. How many moles of zinc do I produce? So we can use the molecular weight and figure out I'm going to produce about 1.53 moles of zinc. We can do the same thing for HCl with its molecular weight and figure out I produce about 2.7 moles of HCl. So in this case, it looks like I have more HCl than zinc. So zinc should be limiting, except for the stoichiometric ratio, because I need twice as much HCl as I have zinc. But do I have that? So in order to check, I can take the ratio of HCl to zinc, which when I divide by the amount of zinc, it turns out I have 1.79 moles of HCl for every mole of zinc. I need 2. So what you can do is essentially when you have the mole ratio you have versus the ratio you need, if the top number, if your ratio is less than that number, then you need more of that top reagent. If that ratio is greater than the number you need, then you're going to need more of the bottom bottom reagent in order to lower the number. So in this case, it turns out our limiting reagent is HCl, because I need a little bit more HCl to hit that 2-to-1 ratio. Now, the other major approach is you can try and figure out, well, exactly how much H2 will 100 grams of zinc produce and how much will 100 grams of HCl produce. So we already did this for zinc. 100 grams of zinc will produce 3 grams of hydrogen gas. We can repeat the process for HCl. Now, using the molecular weight of HCl and the 2-to-1 stoichiometric ratio. Never forget your stoichiometric ratio. It can make a big difference. Because in this case, 100 grams of zinc will make 3 grams of hydrogen, whereas 100 grams of HCl will make 2.74 grams of hydrogen, just slightly less. And since this amount of HCl produces less hydrogen, it turns out I need more HCl to make more product. So HCl is my limiting reagent. So HCl has a lower theoretical yield, thus limiting reagent. Now, what this means is that if the reaction goes to completion, I'm going to have some zinc left over. But how much? So one of the ways you can do this is figure out exactly how much zinc is going to be reacted by 100 grams of HCl. So I know I've got 2.74 moles of HCl. And using the stoichiometric ratio, this means that 2.74 moles of HCl will react with 1.37 moles of zinc. But I have 1.53 moles, as we calculated earlier. This means I've got about 1.16 moles of zinc that will remain unreacted. This is called my excess zinc. We can use the molecular weight to turn it back into grams. And so I'll have about 10 grams of zinc in excess. So in other words, about 10% of my zinc is completely unreacted. It just kind of goes to waste. And this is one of the real ideas of limiting reagents, is trying to figure out how to maximize how much we produce. Now, one of the important features here is that it is worth noting when we have two reagents, we do have two different theoretical yields. This means it can be a little bit tricky trying to calculate your percent yield, because you have to first, before you determine percent yield, figure out which one has the lower theoretical yield and use that in calculating your percent yield. So for example, I've got 100 grams of zinc, 100 grams of HCl, and I produce 1 gram of hydrogen. Well, in this case, I have my actual yield of 1 gram, and my theoretical yield is now 2.7 grams of hydrogen because it's dictated by my limiting reagent of HCl. And this gives us a percent yield of about 37%. So one of the other very cool things is you can use this amount of H2 actually produced to figure out exactly how much zinc was actually reacted and how much HCl was actually reacted. And this will tell you, in reality, how much of both reactants remains. So this kind of brings us to the end of our limiting reagents and basic reaction stoichiometry. Next time, we have to deal with the pesky thing that most of our materials, like this HCl, are in solution. And we need a good way to determine exactly how much of a solution phase species is actually there. So next time, on to solutions, on to molarity. Until then, take care.